Welcome to the world of thermodynamics.
Oh, great.
There are 4 laws of thermodynamics. Zeroth. 1, 2, and 3.
0, 1, 2, 3. What's wrong with 1, 2, 3, 4?
Are you gonna keep talking?
You may be wondering why not 1, 2, 3, and 4.
Thank you.
Well, it turns out the zeroth law of thermodynamics was developed after the first 3. But this law is so important that it was decided it should be first.
I think this guy sounds kind of British.
The laws of thermodynamics were primarily developed by Rudolf Clausius and William Thomson, with the first and second laws being formally stated around 1860. The third law was later developed by Walther Nernst between 1906 and 1912.
Could be Australian.
Be quiet, it's starting.
The zeroth law of thermodynamics states that if 2 thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other.
Are you freaking kidding me?
What?
How is that a law? That's just obvious.
Well, if it's so obvious, why don't you give me an example?
Okay, I can do that. Well, imagine I have 3 pigs, okay? And all 3 of them are equally as stinky, okay?
Stop saying okay.
Let's call them A, B, and C. According to this law, if A is as stinky as B and B is as stinky as C, then A and C are equally as stinky. That's it, isn't it?
Well, I think you're oversimplifying things, but I mean, technically, yes, you are correct.
The first law of thermodynamics states that energy can neither be created nor destroyed. It can only change forms. In any process, the total energy of the universe remains the same. For a thermodynamic cycle, the net heat supplied to the system equals the net work done by the system.
Another obvious one. If I take 100 pounds of clay, it doesn't really matter what shape I give this clay, it's always gonna be 100 pounds. So no matter the shape, the mass remains the same.
That is actually not a bad example. You are right. 100 pounds of clay will always be 100 pounds of clay, no matter the shape.
The second law of thermodynamics states that the entropy of an isolated system not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium.
Okay, that is just gibberish. I'm pretty sure this guy's making things up.
No. Entropy just means the measure of disorder and randomness in a system. This randomness can only increase over time. It can never decrease. It can never go back.
Still gibberish.
Okay. You know how every morning I enjoy a nice cup of coffee?
Yeah, so?
Well, this coffee is enjoyable because it's at a very nice 120 degrees. But what if that coffee wasn't fresh? What if it was like a day old?
That'd be nasty.
Right, because in accordance with entropy, coffee will only get colder. It will not, under no circumstance, go back to being hot. That's entropy.
Okay, so basically this is yet another obvious law. That's great.
The third law of thermodynamics states that as temperature approaches absolute zero, the entropy of a system approaches a constant minimum.
What?
By absolute zero, we mean 0 Kelvin, which is theoretically the lowest temperature possible. This law utilizes several formulas. Below is one of the most common ones. This formula is worth memorizing.
Q equals MCAT, of course.
Q simply means heat energy. M is the mass of an object, of course. C means a specific heat capacity. All objects have different heat capacities. This is why copper is a better heat conductor than wood.
Okay, and how am I supposed to know the specific heat capacities of things?
Yeah, you need to Google that. And finally, delta T means a change in temperature. That little triangle over there, it's the Greek letter delta. It's used in physics, math, and chemistry, but it always means the same thing. It means change.
Like I got a delta on my pants?
Yes, Ignus, like you got a delta your pants.
Yeah, well, anyways, this formula, there's no way it applies to like daily life or something.
That's not necessarily true. I can give you a good example.
Okay, go ahead.
Well, imagine one day you want to eat a cup of ramen noodles.
I love noodles.
Yeah, well, there's a problem. You only have 1% left on your 1-gallon propane tank. Well, believe it or not, we can use this formula to see if you actually have enough fuel to heat up the water.
Really? That MCAT formula?
Well, yeah. If you think about it, you actually have all the information you need. You know you need 30 grams worth of water for the noodles, right? We know the specific heat capacity of water is 4.18 joules over grams Celsius. We know that water comes out of the faucet at a temperature of 22 Celsius. And we know that water boils at 100 Celsius. And we need boiling water to cook those noodles. So at this point, we just take the formula and we do the proper substitutions. In this case, Q is the amount of fuel you need to cook those noodles. M will be 30 grams worth of water. C is the specific heat capacity of water. And delta T will be the change in temperature. In this case, we need to transform 22 into 100. 100 minus 22 is 77.
It's 78.
What?
100 minus 22 is 78, not 77.
Yeah, I knew that. Don't interrupt me. So at this point we just do a little algebra. Celsius cancel each other, grams cancel each other, and we are left with 9,655 joules of energy.
I don't think that's right.
Shut up. 9,655 joules of energy is equivalent to about 9.15 BTUs, which is about 0.00009 gallons of propane. So congratulations, my friend, you can eat those noodles.
How's that possible if...
I said shut up.